Hello everybody, my name is Abhinav Gaddam and I am here to introduce our Capstone project titled Medi-Scan. It is an AI-driven retinal image analysis for diabetic retinopathy. We selected this topic because diabetic retinopathy is rapidly becoming one of the leading causes of vision impairment, especially among diabetic patients. The worrying part is that the most people don't even notice symptoms in the early stages, and by the time they do, the damage is often irreversible. Early screening is extremely important, but the traditional process is slow, requires costly equipment, and needs trained ophthalmologists. This makes timely diagnosis very difficult in rural and under resourced areas. So, our goal was to create a solution that is faster, more accurate, and accessible to everyone. That idea led to Medi-Scan. Our system uses UNet model to segment important retinal regions and a CNN model to classify whether the eye shows signs of diabetic retinopathy. This combination allows the AI to detect abnormalities. We also built a simple Streamlit web interface where users can upload a retinal fundus image and instantly receives an AI generated diagnosis with confidence scores. This makes early screening affordable and easy even without specialist equipment. Overall, Mediscan aims to support doctors, reduce manual workload, and bring reliable eye screening to people who needs it most. Now, my teammate will explain the technical details of our system. Thank you.
This is K. Chanakya. I'm here to explain about basic technical information about my dataset and my code. So we have used Fives dataset. So here, these are the images we have inserted in our there are in my dataset. It contains retinal fundus images and used for blood vessels segmentation. Each uh, each images comes with an expert annotated vessel mask for ground truth. It helps train models to detect tiny and large retinal vessels accurately. The dataset is used in diabetic retinopathy and glaucoma research. It is a benchmark for testing medical image segmentation algorithms. Now, so now this is my code. In this first cell, it basically creates a bridge so you can access, read, and save files stored in your personal drive directly within the coding environment. The second cell, it loads the OS and import the pandas and it defines exactly where the folder is located. The command os.list dir reads the names of every file inside that folder and prints them out so you can verify your data is there. In this cell, this code scans for your folder to find every CSV file and opens them by one. It then shows you a quick preview of first 5 rows and so you can see what is inside in each file. So in the fourth cell, it set up the specific file paths for your training, validation, and testing folders. Uh, it it then lists the contents of each one to verify that your dataset structure is correct and folder are accessible. In the fifth cell, the code verifies your data structures by checking if the train, validation, and test folders exist in your main directory. It lists the contents of the main folder and for each subfolder found, prints the names of the first 10 files so you can confirm that data is present without clustering the screen. In the sixth cell, it set up the data generators that automatically load research to 224 into 224 and normalize your images so they are ready for the model. It also applies data augmentation specifically to the training set to help the model learn better by seeing more variety while keeping the validation and test setup unchanged for fair evaluation. In this cell, the code grabs a single batch of prepared images from the training generator and displays the first six of them in a grid. It allows you to visually verify that your data is loading correctly and lets you see the exactly effects of your augmented settings on the images. In this code, it imports the libraries like NumPy and loads the dataset and displays specific images from your dataset. It gives you the tools to convert image files into numerical arrays so you can visualize and them inspect them individually. Here, a function that randomly selects processes and plots six images from your DR and no DR categories. It then executes this function for your training, validation, and test sets to provide a visual quality check your dataset. In this cell, this defines a function that randomly selects. Sorry. This code imports the essential building blocks needed to construct the architecture of your neural network. It brings to the specific layers for processing images, tools to prevent overlifting, and the optimizer algorithm used to train the model. In this cell, this function builds a three-layer CNN that extracts visual features using convolution layer and pooling while using batch normalization to stabilize and speed up training. It includes a fully connected section with dropout, which helps to prevent the model from memorizing the data by randomly turning off neurons. The final layer used to sigmoid activation to output a single probability score, making it perfect for a binary classification task. Finally, it compiles the model with the Adam optimization and binary cross entropy loss, setting up it for efficient and careful learning. From now, my friend Manugna will continue the code.
Hi, this is Manogna. So here we are starting to build the CNN model. If you come down here, we have a table that says the CNN model summary that lists every layer of our neural networks where we have Conv2D, max pooling, batch normalization, flatten, dense, and dropout, etc. etc. And this table overall describes the full architecture of our DR detection model. If we come down here, we have this block of code where we set the dataset path for validation, training, and as well as testing. So this describes the model, where to find the data, and how to process it. Then coming down here, we have this block of code where the model is evaluated on test data set, and we get the final accuracy as 0.4848. And here we imported few necessary libraries to plot the graphs and also to generalize confusion matrix. And coming to this block of code, we plotted the training and as well as validation accuracy and the loss graph using history recorded during the model training. Coming down here, we have two graphs. The first graph is the accuracy graph, where the model's accuracy has improved, but the validation accuracy has fluctuated a bit, stating that the model struggled to generalize well. And the second graph is a loss graph, where the training loss has decreased but the validation loss has stayed high, stating that the model is overfitting. Here is a confusion matrix and the classification report where it summarizes the how well the model has predicted the normal versus diabetic retinopathy. Confusion matrix gives us the correct and as well as incorrect uh, predictions, whereas the classification report gives us the precision, recall, F1 score, and the overall accuracy where the model has performed strongly. The next will be continued by my teammate Pavan.
Hi, I'm Pawan Kalyan, and I'm here to explain how our current code is finding the results. And if we go to the next part, we'll go to the coding. And the coding part, as my before teammate already explained about the confusion matrix, I will start from this area, like how are the data or the result we are queuing. So here, our first step is the data setup and access. Here, we started by importing a GDON library. This tool is often used to easily download files stored on Google Drive directly into our coding environment, which is commonly used when working with large data sets and platforms like Column. And next, we defined the image locations. So these two lines here defines the exact file paths of a system where the two example retinal images are stored. Here, like we took two images. The first image is a normal image, and the second one is the image which is infected by the diabetic retinal. So in the next slide and the next block of the code, we just took this code section is dedicated to visualizing the two sample retinal images side by side. So this is a crucial step to quantitatively assess the difference between a healthy retina and the one affected with diabetic retinopathy before running the deep learning model. So here so this segment uses OpenCV, CV2, and Matplotlib to prepare and display our retinal images in clear way. So we imported CV2 library, which is essential for computer vision tasks, and the CV2 m.read. So here, this function reads the image files from the paths defined earlier and converts them into numerical arrays, like matrices that Python can process. And next, we use color correction. If we say this color correction format. So before plotting, we must convert the images from OpenCV's default BGR uh, order to the standard RGB order used by most other tools, including Matplotlib. So without this step, the colors in the displayed images would look unnatural, like blue areas would look like red and vice versa. So here, we have to display it by the side by side. So here we use Matplotlib to create a figure and display the images. So this setup display window is 10 units wide and 5 units height. So the output is, so this output is a clear visual comparison of the two most important classes in our study. A healthy retinal image exhibiting signs of, and a retina exhibiting signs of diabetic retinopathy. This visual step confirms our data is loaded correctly and lets us see the pathology our model is trying to detect. Features like tiny hemorrhages or X-rays that are key indicators of DR. And coming to the this next section, this section outliners this the final and the most crucial step. Used the trained convolutional neural network CNN to make a diagnostic prediction of the retinal images. So here, first we take the model prediction and the confidence. So here, this function take two inputs, the image parts and the model CNN, the pre-trained one. And here the image is first loaded and resized to the exact dimensions, like how we given as target size here. Then the CNN was turned on. This is vital role because neural networks require a consistent input size. So this image is converted into a NumPy array of pixel intensity 0 to 255. So we divide the pixel value by 255, this scale, the data down to the range to 0.0 to 1.0. This normalization process speeds up training and helps the network learn more effectively. And next, we come to the making the prediction. So here, in this line, the prediction is equal to model predict model predictor of image in this line. So here we do this line performs the model inference. The prepared image array is fed through all the layers of the CNN model, resulting in a single output value. So, and the next one by is decision threshold. So since this is a binary classification, diabetic retinopathy versus normal, the model's output probability is compared against a threshold of 0.5. As this is binary, the output probabilities must be a number between 0 and 1. So if the probability is greater than 0.5, the model favors the normal class. If it's less than or equal to 0.5, it favors diabetic retinopathy. So we calculate the confidence by always taking the probability of the prediction class. This ensures the confidence always reflects how certain the model is about its final decision. Then next here, then running our diagnosis. So these final lines call the function on our two test images. So the system prints a clear human readable result, the image file, the quantitative assessment of the patient's retinal image. So this function, the final function, encapsulates the power of our AI. It takes a raw image, transforms it into a numerical format the CNN understands, and provides an instant evidence-based diagnosis with a quantified confidence score. This demonstrates the model's immediate value as diagnostic assistant. And after this, to just make it into a front-end development, we did the front-end format for this. So this is our front-end code. This Python script creates a simple web application using the Flash framework, allowing a user to upload an image of a retina via a web browser. This app's core function is to lead a pre-trained deep learning model, a CNN, saved as we saved it as best model.h5, which acts as an AI diagnostic tool. When a file is uploaded, the app saves it, pre-process the image, like resizing and normalizing it, feeds it to the model for an instant prediction, and then returns the diagnosis either normal or diabetic retinopathy, along with the confidence score back to the user's web interface. This effectively turns the complex AI model into an easily accessible online service for medical image analysis. Now, I'll show the final web page of this. So this is a final web page. We created it very simple and minimalistic. And here we can upload an image. So I'm uploading the image from our data set. So I'm applying a image which is already infected by diabetic retinopathy. And when I click the predict, and here it shows the prediction is diabetic retinopathy and a confidence is 99%. And at the same, I'll add one more image, which is a normal eye, which is not infected by diabetic retinopathy. And here it shows the prediction is normal and the confidence is 98%. So this interface is very simple and accessible to everyone. And thank you. And my friend Kushwant will continue the more detailed presentation of this.
Hello guys, I'm here to explain about our project Medi-Scan and AI-driven retinal image analysis for diabetic retinopathy. Our project has some abstract and objectives. Okay, what is the Medi-Scan? An AI-powered system to assist in the early detection of diabetic retinopathy. That is our problem statement. Okay, then what is diabetic retinopathy? As you can see in the video, this is the normal retina of an healthy eye person, and this is the diabetic retinopathy eye of an person who is suffering from diabetic retinopathy. Okay, these are all the current diagnostic challenges. Our solution, which solution we proposed? So, automated and accurate CNN model. We trained an CNN model to give an exact accuracy. So it's cost effective and it is fast and scalable also. This is the literature survey which you don't need, in my opinion. So, proposed system architecture. So, how our software works? So, this is the step-by-step process. So, at first step, the user will upload an image. Second step, the AI model will pre-process the image by 224 by 2. before pixel. Third step, unit segmentation will happen. Fourth step, CNN classification for DR features. And fifth step, final prediction. We use unit for segmentation, CNN for classification. So we use these two technologies. Y unit means it is used for precise segmentation of retinal blood vessels. Impact Y of how unit will help our software. Helps the models to focus only on medical significant areas. What? CNNY also learns to identify complex patterns. CNN. So these are all the data sets and this thing. We achieved an accuracy of 94% with a precision of 93% and F1 score of 94.5%. So these are the loss curves in which we have trained our software to handle. And this is the classification accuracy. These are all the learning outcomes and the challenges we faced. The main challenge was finding the data set and training the UI model for this project. The conclusion and feature scope. The main conclusion is we developed a software which predicts if the user has a diabetic retinopathy or not with an accuracy of 94%. In future, we can integrate this software to electronic medical record, which is also called as EMR systems for seamless clinical flow. Future, we have to expand the model capabilities to detect other retinal diseases. We are also trying for that. We have to try. So any questions, feel free to comment down. These are all the image sources.